Hello, welcome to online lecture of Physics 103. Today in this lecture, I'm going to talk about oscillatory motion. Now we'll be talking about ideal spring and simple harmonic motion. So when I say ideal spring, the spring having no mass, right? Let's take a look at this. Let's take a look at this example here. So in this case right here, the spring is unstrained. This spring is neither compressed nor elongated. Now, in case A here, case A, we extend the spring by amount x. In this case, the applied force is this way, so that restoring force on the spring is Fs to the left. So in the same way, in case 2, if you compress the spring, then applied force is this way, then the spring force will be this way. Okay, so if this is plus, this is minus, right? All right, applied force causes the change in length of the spring by amount x. Okay, so then this x can be related to the applied force. The x can be related to the applied force by using this relation. So as you know, the Hooke's law is given by Fs equals minus kx, and in our case we have negative sign because we have spring force, but in this case applied force, that's why we have positive here. Okay, so in this slide I'm going to introduce the oscillation, which is a repetitive motion. So if you have a spring like this, a mass is hanging, right? This is the center of the yellow thing there is, this is the center of mass of the hanging object. Okay, so this yellow thing is oscillating up and down. As you can see here, if you take a look at this yellow thing, it's oscillating up and down. But in the same way, in the time scale, if you look at the time scale here, so this yellow thing is moving along the curve, which is called sine curve. Okay, this curve is called sine curve. As you can see here, the yellow center of mass moves along the sine curve. That's why this kind of repetitive motion is also called sinusoidal motion. Okay, in this kind of motion, I'm going to define the frequency. Okay, so definitely this is oscillating motion, and in oscillating motion, what is the frequency of an oscillating motion? Frequency is the number of oscillation per second. Suppose when I say oscillation per second, so what is the oscillation? So you have the sine curve here. If you go look at the yellow mass going from this top to this top. Okay, by the way, they are called crest. Okay, both of them are called crest. Okay, these are exactly the identical points of the sine curve. Okay, and they are the top part of the sine curve, the highest peak of the highest point. These two are the highest point of the sine curve, and they are called crest. When the yellow point goes from here to here, that's the complete oscillation, one complete oscillation. In 1 second, how many oscillation is happening? That's called frequency. Looks like in this case, in 1 second, we have two oscillations per second. Okay, if that is the case, then frequency f is equal to 2 hertz. Now, in this case, I'm going to talk about the time period. Okay, what is the time period? Time period is the time taken for one oscillation. Okay, in the previous slide, we have two oscillations. Take 1 second, right? Then what is the time for one oscillation? Meaning one oscillation take how much time? That time is called time period. Okay, time period. And time period is denoted by T, big T. Okay, so like if you go to grocery store and you want to buy in $2 If you go to grocery store and in $2 you get 6 banana, then in $1, how many banana you can buy? You divide 6 over 2, which is 3 banana, right? 2 oscillations equivalent to 1 second. How about 1 oscillation equivalent to? One oscillation is equal to 1 over 2. How do I know? Divide this by that. In this case, we divide 6 by 2. In the same way, here we divide 1 by 2. Okay? So this time for one oscillation is called time period, right? So then what is the difference between time period and frequency? The frequency is 1 over t, or t equals 1 over f. You take the reciprocal of time, you get frequency. You take the reciprocal of frequency, you get the time period. Okay. So, by the way, in this kind of oscillatory motion, the spring motion in this case, right? So, time period is given by this formula. Okay. Let me define the quantities involved. T is time period. 2 pi is a number. Then you have the square root. Then m is the mass of the hanging object. In this case, this red mass. Remember, we consider the mass of the spring to be 0. So as compared to the hanging object here, the mass of the spring is 0, which is very light. That's why we can simply neglect the mass of the spring. Okay. So in this case, m is the mass of the oscillating object, in this case red object, and k is the property of spring, and that is constant, okay, for a particular spring. All right. So this is the time period. Then how about the frequency? You just take the reciprocal, right? Frequency is reciprocal of time. So in this case, 2 pi goes on the bottom, and here they flip, right? So k over m. Okay, that's what this guy is. All right. So by the way, this kind of repetitive motion of the spring is also called simple harmonic motion. Okay, simple harmonic motion. So in this example, the mass undergoes simple harmonic motion without damping, meaning the amplitude does not change with the oscillation. Okay, for every oscillation, it goes through the same height, right? Up and down. Okay, there is no damping. If the shock absorbers in a car go bad, then car will oscillate at the least provocation, such as when going over bumps in the road and after stopping. Calculate the frequency and period of these oscillations for such a car if the car's mass, including its load, is 900 kilogram and the force constant K of the suspension system is this much. Okay. In this case, we have to find the frequency. All right, let's find what is the formula for frequency from previous slide. Frequency equals 1 over 2 pi, okay, k over m. All right, so then let's plug in the values, right? So if you plug in the value, what do you get? 1 over 2 pi. 2 pi means 3.14. Then k, what is k again? K is given here, 6.53, 10 to the 4. Then you have m. What is the mass? Mass is 900 kilogram. Okay. Make sure all the quantities involved have same system of unit. In this case, mass is 900 kilogram, which is mks, and this is also mks, Newton meter. So that's why we have everything in mks. So now if you do that, you happen to get the frequency to be number. I'll give you the answer here. This hertz. If you know the frequency, then what will be the time then? Calculate the frequency and period of this oscillation. So we know the time frequency. Now let's figure out the time, which is 1 over f, right? So this is 1 over 1.36, which is equal to 0.738 second. Okay. Now in this case, we define the elastic potential energy. So elastic potential energy is the energy that a spring has by virtue of being stretched or compressed. Okay, so suppose you have a spring here. This is the original length of the spring. Okay, if you stretch it, then the spring has potential energy. If you compress it, it has potential energy also. How do I know? Because if you stretch it up to here, and if and you release it, then the spring will go to this position, right? Why is that? Because when you stretch it, the spring has the energy, because it is that energy that brings the spring to its original position. Okay, similarly, if you compress the spring like this, and after some time if you release the spring, then what happens is the spring come back to the original position. Okay, why is that? Because spring has an energy. Okay, that because of the energy of the spring, it will come back to the original position. Okay, meaning when spring is stressed or compressed, the spring has the potential energy. Okay, so the spring has an energy. That energy is called potential energy. Okay, so the potential energy of spring is given by 1 over 2 kx squared. By the way, this kind of potential energy is also called elastic potential energy. Okay, so if there is extension or compression, if there is extension or compression, then there will be potential energy. Okay, as long as x goes 0, P becomes 0. Okay, keep that in mind. So what is the unit of elastic potential energy? Again, it is joule, because it is energy. So let's do a problem here. We can use a toy gun's spring mechanism to ask and answer two simple questions. How much energy is stored in the spring of a tranquilizer gun that has a force constant of 50 Newton per meter and is compressed 0.15 meter? Okay, so this you have a gun system here. Okay, you have a gun here, and you compress by your x equals 0.15 meter, and of force constant of the spring k equals 50 Newton per meter. If you neglect the friction and mass of the spring, at what speed will 2-gram projectile be ejected from the gun? Okay, so first of all, you have to find the how much energy stored in the spring. Okay, so from previous slide, what is the what is the potential energy? Potential energy is 1 over 2 kx squared. So 1 over 2 k is 50, right? And x is 0.15 square. So if you do that, you end up getting 0.563 joule. Okay. Now part B says if you neglect friction and the mass of the spring, at what speed will the 2-gram projectile be ejected from the gun? All right. So let's take a look at this picture B and C here. In picture B, what happened is we compress the spring all the way here by amount x. Okay. So I call this is the position 1. Okay. Then I call this position the position 2. Okay. At position 1, what is the potential energy? Potential energy is given by 1 over 2 kx squared, because this is the x, because the spring is compressed by amount x. That's why potential energy, let me call potential energy 1 equals 1 over 2 kx squared. Now, when the spring, in the case of picture C here, in picture C, so what is the extension in this case? In this case, extension is 0. So that's why potential energy is, I call potential energy 2, which is 0. Okay. Again, let me go back to the position 1. What is the kinetic energy there? Kinetic energy, right? At this position, the bullet is not moving, or projectile is not moving. Projectile is not in motion. That's why kinetic energy is 0. How about kinetic energy in this case? So in this case, kinetic energy is non-zero, because the bullet has moved distance x already, right? So that's why potential energy is not 0, because bullet has already moved and it has certain velocity. That's why kinetic energy is this. So what is the total mechanical energy here? Total mechanical energy is PE1 plus KE1. Since KE1 is 0, you simply have PE1, which is 1 over 2 kx squared. Okay. Similarly, what is the total mechanical energy in this case? PE2 plus KE2. What is PE2? 0. What is KE2? 1 over 2 mv squared. Then you get 1 over 2 mv squared. Okay. So total mechanical energy is constant, right? Conservation of principle of conservation of energy. So these guys 1 and 2 has to be equal, meaning 1 over 2 kx squared equals 1 over 2 mv squared. So divide both sides by 1 over 2. You cancel out 1 over 2, 1 over 2. Then you got kx squared equals mv squared. Okay. So let's use this formula and figure out the V. Okay, that's what we do. Divide both sides by m. What do you get? M cancel out. Then what is your V then? V equals k over m, kx squared over m. This can be written as kx, k over m x. Okay. Now you can simply plug in the value of k. Now let's plug in the let's go to the let's simply plug in the value of k, m, and x. So v equals k, m, and x, right? So k is how much? K is 50. M is how much? Now you have to change the mass to kilogram, right? Because gram has to be changed to kilogram. 2 10 to the minus 3 kilogram. Then x is how much? 0.15. So if you do that, you end up getting 23.7 meter per second there. Okay. In this slide, we'll be talking about a pendulum. Okay. So rather, it is a simple pendulum. So a simple pendulum consists of a particle attached to a frictionless pivot by a cable of negligible mass. Okay, so you have frictionless pivot here, and the cable is negligible, and you have a mass here. This pink one is the mass. So by the way, this pink mass is called bob, B-O-B. Okay, bob. All right. All right, so this simple pendulum oscillates to and fro, right? It has to and fro motion, and these two positions are called maximum point. Okay, as you can see here, and the center point is called equilibrium point. All right. So in the case of simple pendulum, the time period of oscillation is given by 2 pi L over G. Okay, 2 pi is constant, as you know. 2 is number, pi is 3.14, and L is the length of the cable. Okay, the length of the cable here, this is L. Okay, length of the cable, you can see here. This is the length of the cable, and G is acceleration due to gravity, and G is acceleration due to gravity, and on the Earth's surface, G is equal to 9.8 meter per second square, right? So let's do a problem here. All right. So determine the length of a simple pendulum that will swing back and forth in simple harmonic motion with a period of 1 second. Okay. In the case of simple pendulum, the time period is given by 2 pi L over G, right? So if you square both sides, squaring both sides, what you get is t squared on the left and 4 pi squared L over G, right? We need to find L. So multiply both sides by G and divide both sides by 4 pi squared. You got this cancel out, this cancel out. Then you have L equals GT squared over 4 pi squared. If you do that, plug in the value now. 9.8 t square is 1 square divided by 4 pi square. 4 times 3.1 squared. If you do the calculation, you get the value equal to 0.248 meter. All right.